60 seconds.
Okay, great to have everyone here today for this webinar, 5 ways to identify savings on the paper machine. For those of you who don't know me, my name is Russell Allen. I'm the owner of Aurelia Group Consulting. Before starting Aurelia Group, over the last 10 years or so, I spent another 25 years in the paper industry. And right at the moment, I'm the editor for the Appetite Journal, the Australian technical journal for our pulp and paper industry. Before we get started, it's usually good to make sure everyone is connected and working. So if you'd like to go to your chat box on the right-hand top side of your screen and type in where you're listening from, that would be great. It'd give us an idea of where you are. Okay, so we've got people from Melbourne, from Sydney, Brisbane, someone from Atlanta, which is great to have you on board. Terrific. It sounds like we're all set to go. Now today I want to take you through some opportunities that we identify on the paper machine. And to do that, I need to start by developing some of the unique tools we have found and developed ourselves for our group to do this. And these tools are really based at trying to get good information more quickly than we would normally get it. So if you like, we want to be more effective and we want to see cause and effect, and we want to do it very quickly. So just before we start, let's have a look at the sort of opportunities we might see today on the paper machine. Well, let's have a look at them in order. This plot gives them in order in terms of potential $1 million savings per year. The first one is accelerate trials, and there we're looking at making the trials easier, faster, and less risky. The second one is to minimize reject paper. We all have rejects in our paper mill, but how do we identify them and how do we treat them? If we can improve that process, we can save a lot of money. Thirdly, we can lower cost inputs. If we understand what's happening to our inputs and how they relate to how paper performs, we can lower those inputs potentially. Fourthly, we can improve starch performance. A lot of paper machines use starch. It's an expensive component. So maybe we can save starch performance, and in a lot of cases we can. And then finally, perhaps the big one, there's the potential to downweight but still have the minimum performance that we need. So that's where we're going to go today. Let's go on to our next slide. There's 3 tools that we want to apply today that Aurelia have developed. The first one is an online TSI stiffness measurement. And this is a single point measurement that sits on the paper machine. It's currently being redeveloped and improved as well. So it's very exciting for us, this particular development. But what it does is continuously measure properties like ring crush and SCT, burst, things like that. Concora crush, it can measure as well or predict. And you can see on this slide a comparison between top of reel measurement, which is the brown trace on the left, and the PQM measurement, which is the green trace. And this is over a 700 roll sequence. And you can see that the correlation is very good, very useful. The advantage of the TSI measurement is that we can measure a couple of times a second as the paper's being made. So we know what's happening within the paper reel. And also, because of the amount of data we get, we can be much more confident about the result. And that's very important, say, when we want to run trials. The other thing I want to point out is that the plot on the left is plotting an indexed property. We prefer to plot an indexed property because that represents the true material property. That's the property divided by the basis weight. A lot of people plot graphs that are just, say, CD ring crush, not indexed, and what you're really seeing is the relationship between basis weight and the property. Well, we don't feel the need to do that because our predictors are so good. When we look at top of reel, and this will appear very blurry to you, when we look at top of reel measurement, we don't get the complete picture because there are a lot of trends and a lot of things happening as we go through our measurement that we don't pick up on top of reel measurement every hour, every reel, every 2 hours. So this is really the sort of picture we get presented graphically. It measures paper quality every hour or two. There are low test rates, and that means that the picture we get of the paper machine performance is blurry and it's not representative. What we would really like is to have the full picture and a detailed picture. The TSI measurement measures paper quality every second of every day. It gives a complete picture of paper quality, and in some cases, as you can see, it's important to know the complete picture. The comparison between the blurry picture and this less blurry picture, a real one, in that what we've done is calculate the resolution of, say, getting a measurement once a reel and calculating the resolution that we provide with the TSI measurement. And so in that sense, it gives you a good idea of how the picture's changing. The second tool that we would apply is related to functional property predictors. So functional property predictors are predictors that we undertake based on our fundamental TSI measurement on the machine. Now, functional property predictors are different from the normal curve fitting in that we are using physical relationships that describe the property in question. So in that sense, instead of just fitting a curve fit to data that we have, we are trying to understand how the property works, how performance works, and then we use that as our predictor. And you can see in this case, for STFI index or SCT, for a number of different types of furnishes, 100% long fibre through to 100% recycled, the different colours on that plot, the correlation is very good and very useful. Now, we don't always have to use it with our TSI measurement, our online measurement, because just understanding the property gives us some insight into what has to happen on the machine to, say, improve or change a functional property. If we change one property, we may change another one, so we need to understand the interaction as well. So that's another tool that we apply to the work that we do to save money on the paper machine. The third tool I want to apply today that we're going to need is ZD stiffness, or through thickness measurement. Now, pretty much everyone in our industry is used to the MD and the CD TSI measurement. This is a technology that was really developed by IPST in the United States some years ago. And it's looking at measuring the same thing as TSI, but this time it's doing it in the thickness direction. That means it gives us the possibility of having MD, CD and ZD TSI, the three dimensions of performance in the material, which of course is an additional bit of information. So we use the ZD thickness to look at where starch resides in the sheet, how effective starch is in the sheet, whether forming is appropriate for a particular product or property, and for calculating the effect, and we'll see this later, the effect of the profile down through the thickness of the sheet on different types of property. So very valuable technique that we apply. Okay, so having got across the tools that we're going to apply to try and save ourselves some money, let's look at our first opportunity, and that is, let's accelerate some machine trials. Now, normally machine trials take perhaps a shift, maybe a bit longer, maybe a shift and a half, 2 shifts, and the performance, the product quality is a bit risky. So really, we're going to have to be prepared to give away some of that quality as well. The advantage of measuring every second as the reel is being built up is that we can see trends very quickly, and we can collapse the time scale of the trial. I mean, I think that makes sense. So spend a second and have a look at this plot. The blue line represents the top of reel results for MD-CD tensile ratio, and this was a rush drag trial on a paper machine. The red trace represents the online stiffness tester, PSM4, that we used during the trial. And apart from the fact that you can see that they correlate very well, hopefully you can see that there's a lot more detail in the red trace and a lot less high scale variability. This means that we could do a rush drag trial theoretically within a reel if we're able to change the rush drag setting fast enough, because you're measuring every second, at every second. The other really great thing about this plot is see how the red plot, as the MD-CD tensile ratio drops from 2.3 to 1.8, can you see how the noise, the fast frequency noise, gets greater? That's real property variation. As the sheet gets squarer, we all know that the sheet and runnability gets less stable, and you're actually seeing it in real time here. So probably there's an optimal point that you would want to operate to minimize that instability on the paper machine while getting all the properties and squareness that you're after. Here's another example how we might be able to accelerate machine trials. Refiner trials. In this case, we're looking at burst strength, and you can see when the refiner trial started. And it's clear from the blue trace, which is the continuous measure on the paper machine, that there was some effect, although it was pretty small, 660 to about 680, so 20 units. That's very hard to see top of roll measurement, because the top of roll measurement has a lack of confidence associated with each measurement, and it doesn't necessarily mean that it's representative. So what that means is you have to do a lot more top of roll measurements to try and decide whether a refiner trial is working or not. Well, that's wasteful, that's risky, and there's no guarantee at the end of the trial that you'll have a conclusion that you can use. Whereas the blue line, which is the continuous measure, every second we're measuring that, and you can see the trend is very clear. So typically on a paper machine throughout a year, I would say that you could well save about 1/3 of a million, 0.3 of a million a year by accelerating, compressing the trials that you run on the paper machine. And that's not looking at how the effectiveness of the trial ultimately brings profitability to the paper machine. Have a look at this trace. This is one of the outputs from our online TSI measurement, MD-CD. Everyone has rejects. Everyone has some percentages that they allow to be below quality, and they hope to drag back in so they can ship it and make money from it. In this case, there are two traces, a red trace and a blue trace. The red trace is burst measurement, and the blue trace is a ring crush measurement. The dotted traces are the top of reel measurements. They're properties that were measured top of reel. And the big thing to see in this trace is that despite the large change in the burst value, one reel, one measurement, which would probably mean that you'd have to measure before and after that reel to make sure there wasn't a quality problem. If you look at the continuous measurement, you can see that there was no issue with the performance and with the quality. So pretty much you can say, yes, I measured this top of reel, but I know from my other continuous measurements that there is no quality problem. I don't need to reject this reel. Now that saves a lot of things. 1% of manufacturers set aside generally on a paper machine, and 60% of this is ultimately found to be okay and shipped. Now, interestingly, statistically, the opposite is true. 1% of manufacturers set aside, but it's possible that 60% of that 1% is not actually identified as being reject and is shipped anyway. So there's a quality problem in itself. So to minimize rejects and to save money, we're minimizing delay, we're minimizing rework, we're minimizing additional testing, and we're minimizing waste. So all in all, on a typical, say, packaging paper machine, sort of saving you're looking at here would be about $1 million a year. So that's not just change, is it? The third way of optimizing cost on the paper machine is starch optimization. A lot of paper machines use starch either in a size press, a speed former, or at the wet end as cat starch. Understanding how starch works on different machines for different furnishes is very, very important, because starch is a significantly expensive component. Necessary, but it's a significant cost to the paper machine. So if we can optimize that and control it and get the best out of it, we can save money. The plot on the left shows you percent property improvement against percent starch on fibre. Spend a second or two to look at that. Okay, what you can see is that the property improvement is you add starch, say, to 0 to 10%, which is the scale on the horizontal axis of the plot. As you add starch, you get a significant improvement, and then it starts to roll off. That's typical. That's a typical shape of a starch effectiveness curve. What that means is that beyond a certain point of starch addition, you're really not getting much benefit from the starch addition. Here's a plot of the starch profile through the thickness of the sheet. So along the bottom, we have the thickness of the sheet, or the depth through the thickness of the sheet. The blue curve represents the percentage starch on fibre in a size press mode. So it goes from 12% at the edge, it goes to 0 around the middle of the sheet, and it's not symmetric in this case, so the blue line only goes to about 7%. On the back of the sheet. Now the brown line represents the percent improvement that we would expect to get from that blue line, or the concentration of starch within the sheet. So again, you can see that it's not absolutely symmetric. Now here I've got 3 different profiles of starch in the sheet. We measure this by using a ZD TSI measurement and layering the sheet. The way we would do it is, well, it's a quick method to give us a good idea, and it's been shown to be very reliable and useful. But here we've got 3 different profiles for the same sheet. All of them have 3% starch on fibre added to them total. And along the bottom axis is the depth, the thickness. And what we're doing is slightly modifying the shape of the profile. And we do that by optimizing the starch viscosities, pressures, nip pressures, and some of the sheet properties to make sure that we get the best arrangement, the best ingress of starch we can. So if we were to look at the properties, and we'll use the red line, the original red line, as the reference, if we look at the original properties, what we can do is compare for different properties what the effect of the different profiles would be. Just have a look at that for a sec. So we have property, and then example 1, example 2, and example 3. They represent the different profiles. So for tensile, compared to the red profile, we would expect a 6% improvement with the blue profile and a 13% improvement with the grey profile. So clearly the grey profile, which is symmetric and has starch going a little bit further into the sheet, is better for tensile. If we look at bending stiffness though, and we use some of our prediction relationships, what we see is much less change across the way. So our expectation would be, in this instance, that if we had these different profiles, our changes in performance for bending stiffness would be minimal, really hardly measurable. So it depends on understanding which property you're trying to improve. There are ways of improving bending stiffness with starch addition, say at the size press, but you need to understand how to optimize those. Here's an example of how the PSM measurement might be used after you've come to grips with how the starch is getting into the sheet. And it represents another trial, a size press trial. Or actually, in this case, it's a cat starch trial. And we're looking at burst, which is a very common property, of course, for packaging papers. Where the black arrow is where the starch trial started and starch was increased. And the red dots represent top of real data from the machine lab. The blue trace represents continuous data from the PSM unit. And you can see that the red dots are very noisy, and it takes quite a while to really convince yourself that there's been a change with the starch increase. However, the blue trace comes up very quickly and plateaus out as expected. So again, this is a way of compressing and accelerating the trial period. So all in all, attacking the starch use on the machine, looking at increased performance and taking value as a result, around $2 million, $2 million a year by looking at that carefully and adjusting it and optimizing. Okay, strategies 4 and 5, they're really related. So take a second to look at this plot. It's a plot of percentage property against time. Now the red lines, the dotted lines, they represent the top of real result. So, I mean, for all intents and purposes, when you take a top of real result, that's the result until you take the next top of real result. And that's how it's presented on this graph. The blue lines, they represent continuous measurement. That's what's really happening in the real and across the roll. And you can see that there's quite a significant trend from about 100 minutes in. So what we're really trying to say is that there's variation there that can be attacked if we can see it, and if we have actuators that can actually control it. Now you might be surprised to see that it's come up on the screen that 15% peak to peak variation is common within a reel. That's of a property, and we're not talking basis weight or moisture, we're talking ring crush, reel burst. Also, if we look at subsequent makings of the same grade, then you're looking at 25% peak-to-peak variation across makings. 25% is a lot of variation. If we can attack this and lower that variation, there are cost savings. A lot of people will tell you, yes, we know there's variation when they're challenged about property variation on the paper machine, but they say it all happens too fast for us to do anything about it. In fact, about 50% of this variation is slower than 2 hours, and we can attack it, we can optimize it, we can change it. What we have to be able to do is measure it and have strategies in place to make those changes. Here's a great plot. Have a look, it's pretty busy. Have a look at this plot. This was a great result for the mill we were working at. You can see it on the left there, set up under the sheet, the sensor. The top plot, the blue plot, is CDSCT as we would measure it. Then there's CD velocity, which is measures, and then the green is the MD-CD ratio as we measure it, and then finally the red is burst as we measure it. So they're continuous plots, and they go for, I guess, probably 4 or 5 hours. But the interesting thing about this is that there's a shift change at 8 a.m. and you can sort of, the red line represents the shift change, the red dotted line, vertical dotted line is the shift change. And the great thing about this is at the shift change, and you can see the issue here is that the blue line has a very cyclic response in SCT, and clearly it's coming from the MD-CD ratio. So there's in the green, which mirrors that oscillation, and it runs up to the shift change. And so obviously there's a forming issue, MD-CD ratio and instability in terms of MD-CD control. So the shift change comes, and all of a sudden the operator does something which removes the oscillation completely. He's still got a problem though, and that problem is that his average value for the sheet is now below the average value of the sheet with the oscillation. So he now makes a pretty significant change, nearly a perhaps 18% change to MD-CD ratio. You can see it in the green drop, and then starts to bring it back. And as he does that, the CDSCT, which is his primary measure, starts to come up, and now he's back in play make a good quality board. I think this guy deserves a medal. He knows what's going on his paper machine, and he's very quick to set it up. He should get a bonus. So if we wanted to be a little more rigorous about this variation thing, here's some plots which represent sequential makings. So these are of the same grade. So these are grade makings, say 1 grade making, and then 2 weeks later, back it through the cycle, the same grade being made again, and then the green plot here, same grade, and then the 4th same grade, but made subsequently, consecutively as that grade. And you can see, and this is a distribution frequency of reels vertically, and you can see that the mean and the distribution, the variation, if you like, in this case of seed ring crush, changes a lot. And this is the variation that we want to try and minimize. And where we get an advantage is if we can do this. Here we've got the same distribution, but what we want to do is squeeze it down and narrow it all down. And there I've shown it as the old aim. And then having done that, we want to move that whole distribution down to a new aim. And that's worth basis weight, and it's worth dollars. While we're doing that, we want to ensure that our minimum performance, the minimum performance that the customer sees, is maintained. Because ultimately, it's the minimum performance the customer sees that controls his perception of quality, and in fact controls the quality and performance of the board we're making. So, strategy 4. Let's use these ideas now. While maintaining minimum performance, if we could lower the variation on the paper machine, and we're saying we can now, we can identify it, and there's a lot of variation on the paper machine that's slow enough for us to do something about if we can measure it. So while maintaining minimum performance, we can do a few things. We can replace virgin fibre with recycled fibre in some cases. When we do that, we can decrease refining. When we do that, we can increase express dryness and production rate, and we can lower starch usage. So, what's it worth? Well, on a typical packaging paper machine, it's probably worth about $3 million a year, with a concerted effort to minimise variation, move the aim, and meet the minimum requirements still. Now, the big advantage of this approach is that you're not changing basis weight. So for those people who are constrained by basis weight considerations with their customers, this is one way of taking good savings out of the paper machine. Finally, and probably the best in the sense of how do I get cost savings out of the machine, while maintaining minimum performance, we take the difference between the old aim and the new aim, the difference that we get from minimizing variation, property variation on the paper machine, we take that and we just lower the basis weight. And typically we can there's enough variation we can attack on the paper machine to lower the basis weight by about 5%. And 5% is around $5 million a year. Now, the disadvantage of that is that you are lowering the basis weight, so customers who have contracts with you for basis weight may have a problem. The advantage of it is that your production rate goes up, your refining costs lower, your machine speed increases. There's lots of obvious benefits when you would have all been through that yourselves. So, we get to the end of the seminar, the webinar, and there's a 6th strategy that we have to offer you, and that is some sort of free assessment. What's the assessment about? It's an opportunity assessment. Let me put up a slide for you to give you some details. So, free opportunity assessment, in real terms, it's worth around $5,000. That's what we would normally charge for this assessment. It will benchmark your performance against global performance. It'll apply our unique knowledge to your operation and your test results. It's a limited offer. It'll only be on for so long, and there are conditions. So the way to get involved in this is to go up into the right-hand side, into your chat box, and say, yes, I'd like some details about this. In any sense, we'll be sending an invitation and some information out to those who have shown interest. So I hope you've enjoyed the webinar. I hope it's given you some food for thought and some information that you may not have had available to you before.